In 1819, Hans Christian Ørsted discovered that electricity has a magnetic effect. The figure shows a compass pointing in a north-south direction. Click on the switch once. The compass needle will deflect and point to the west. The compass needle will deflect and point to the west. What happens to the deflection of the compass if the direction of the current is reversed? Click on the cell to reverse the direction of the current. Then, click on the switch to see what happens. The compass needle will deflect and point to the east. Can you see the difference between these two circuits? When the direction of the current is reversed, the compass needle deflects in the opposite direction. This experiment shows that a magnetic field is produced when current flows through a wire. This is called electromagnet. Finding the shape of the field. We can plot the magnetic field pattern of a current-carrying straight wire by means of a plotting compass. Drag and drop the small compass onto the card. Click on the switch to find the direction of the magnetic field lines. The resulting magnetic field lines are a series of concentric circles around the wire. The right-hand grip rule can be used to determine the direction of the magnetic field. Grip the wire with the right hand, with the thumb pointing along the direction of the current. The fingers will curl in the same way as the direction of the magnetic field. What happens when the direction of the current is reversed? Click on the cell to reverse the direction of the current. Then, click on the switch to see what happens after this. We can use the right-hand grip rule to determine the direction of the magnetic field. As the direction of the current is reversed, the direction of the magnetic field will also be reversed. A dot in the wire shows current flowing out of the paper. A cross in the wire shows current flowing into the paper. The strength of the magnetic field is greater when it is closer to the wire. The strength of the magnetic field also depends on the magnitude of the current flowing through the wire. The larger the magnitude of the current, the greater the strength of the magnetic field. Magnetic field pattern of a flat coil. We can use a small compass to find the direction of the magnetic field. Drag and drop the small compass onto the card. Click on the Start button to find the direction of the magnetic field lines. Can you see that the magnetic field is stronger at the center of the coil? This means that more magnetic field lines per unit area lie on the inside region of the coil. Note that the field lines at the center are straight and perpendicular to the plane of the coil. We can increase the strength of the magnetic field at the center of the flat coil by increasing the current. We can also increase the number of turns of the flat coil. Magnetic field pattern of a solenoid. We can use a small compass to find the direction of the magnetic field. Drag and drop the small compass onto the card. Click on the switch to find the direction of the magnetic field lines. Can you see that the magnetic field of a solenoid has the same shape as the magnetic field around a bar magnet? Hence, the solenoid can be said to have poles. If the current is flowing in an anti-clockwise direction, it shows that the end of the coil is the North Pole. If the current is flowing in a clockwise direction, it shows that the end of the coil is the South Pole. The strength of the magnetic field can be increased by A. Increasing the current. B. Increasing the number of turns per unit length of the solenoid. C. Placing an iron core within the solenoid.